So good afternoon, everyone. So today we have Christopher, our postdoc, to give a talk. And he received his PhD from University of Hawaii. And he worked on his thesis project with microcolony and ball rippers. And he's expert in the infrared and optical spectroscope of young stars. He also worked on ALMA data recently. So today he's going to introduce about his spectroscopic study of young star, and which have an important implication of star formation. So yeah, welcome our speakers.
All right, thank you, Siri, for that nice introduction. So today I will talk to you about how magnetism affects the stars, young stars, in their surface. So this is not related necessarily with how they affect their circumstellar environment, but actually the stars themselves. And I have a pretty picture of the sun right here. I guess we are all familiar with this one. Just to tell you that magnetism actually happens in so many stars. The sun is one of them, and they actually have implications for their evolution and the properties we measure. So, first thing I should say is that mass is maybe the most important characteristic of stars. Mass is set during the protostellar phase. In less than about 1 million years old, the mass of the star will be set. If you do not acquire enough mass to become an actual star, you will become a brown dwarf, and then you're going to contract and you're going to cool down for the rest of your life. If the star acquires more mass, like the sun, for example, you will go through different phases: a red giant, eventually become a planetary nebula, and a white dwarf. And if you're a very massive star, you might end up as a supernovae and becoming one of these very interesting objects like black holes or the neutron star. Okay, so it's really mass what sets the path of the stars. That's why it's so important. And it's not only that. As you can see from this very nice cartoon, mass will also set the temperature of all these stars, which is represented here by colors, and it will also set the size, which is the radius, right? So that's also represented here. And mass will actually influence so many other things in astronomy, in many other fields. For example, the mass of the star will set what's the internal structure of the star for a given age, for a given evolutionary stage. Mass will influence, for example, our studies of the IMF. It will also set, if you are trying to measure abundances or metallicities in stars, you have to know what's the mass or the temperature first. And even if we're doing exoplanet research, we know that we can only measure the precision of the mass of a planet relative to the mass of the star. And if we're going to measure the radius of the planet, for example, transits, we know it's going to be related to the radius of the star. So the mass that sets many of these physical properties in a star, it will also indirectly influence so many other studies in the areas of astrophysics. So it's very important that we can have a reliable way of measuring masses and a very precise mass measurements in here. Okay. Mass set the temperature of the stars, the same with the radius for a given age. But the way we measure masses is actually kind of the other way around. We first measure the temperature of the stars, that's kind of the most common way, and from that we can infer what's the mass of the star through some modeling. So we measure the temperature, we use some models, and we get the mass. By temperature, I actually mean very often spectral classification. So in astronomy, we use the NKS system, which is the OV, AF, GK, M classification of stars, and this is basically related to the temperature of the sources because that will set the strength of different lines in the spectrum. For example, if we have a relatively hot source of a B or A type star, a temperature of about 10,000 kelvins, then we should see very strong hydrogen lines. And this is precisely what we see when we use optical spectroscopy, where we can see very, very strong hydrogen lines in the spectrum of these D and A type stars. If the stars then are a bit less massive than that, for example, like solar type, which is a G2 type star, we should see some of the metallic lines, like calcium and iron, and other of these metal lines, and we can see that for solar type stars, we see many more metallic lines, right? So it's this kind of forest that appears here. And if we have even cooler sources like M dwarfs, we should see titanium oxide and other molecules. It's much cooler, therefore the atmosphere can hold some of the molecules. And we can see that for the M-type stars, these are much cooler, about 3,500 Kelvin. Okay, and something that is very important is that for about 100 years we have been developing, or we have developed very early on this spectral classification system, but we have been using it for a very long time. And because of the technology available, it was mainly determined in the optical. Okay? And something that is important is that it doesn't matter exactly where, in what specific wavelengths we measure the spectral times. It doesn't matter if it's in the U, V, or R band. It should be consistent. So if we measure the spectral type in the V band, it should be consistent with the R band, because those two are tied to the temperature of the star, the effective temperature, and that to the mass of the star. That should be all very consistent. Okay? And in star formation, in particular, we also use this spectral classification. I do star formation, which means we are mostly going to be looking at young stars, which some of them have disks, and sometimes it's really hard to determine their temperatures using photometry. So what we use is spectroscopy. So same as people do with the main sequence phase, the main sequence phase, or post-main sequence phase, as I show, we're going to be using spectral classification. This is just one example of an old paper from 1989, where they were doing classification of spectral types of young star sources. T Tauri stars and young stars typically going to have classifications F, G, K, or M spectral types. Now, there's some, of course, more recent studies. This is Hertz and Hillenbrand, 2014, where they also use spectral type to tell what's going to be the temperature of all these young star sources. Now, there's something actually very curious that somebody noticed very early on in the 1890s, at the beginning of the 1990s, and that's a quote by Claude Berthold that I just want to share with you. So what's interesting about this quote is that even this early on, people noticed that for young stars, there was something weird about spectral classification and wavelength dependence. So it shouldn't be this way. The spectral classification should not matter where it's measured at what wavelength. But it was noticed, and this is something you will typically will not find in a paper. And because, as I say, this is something that people knew in some way. Maybe it was too early on, not enough infrared spectrograph to really tell what was happening. But at the time, there was mainly a few theories of what could this be. One idea was that because the stars are still growing, they are accreting some material coming from this that will impact the surfaces of the stars, creating hot regions. Those hot regions can create an excess continuum emission that will change the shape and the depth of the photospheric absorption lines. And if that's the case, then they thought, well, maybe that's affecting our classification at different wavelengths. Another explanation was basically that we are looking at binaries. So maybe there's two stars there, and we're just getting confused when we try to spectral type them. Maybe we're looking at one wavelength, it will do more like one spectral type, different wavelength, just different type of star. But the more we do research, we're pretty sure that some of the sources that still share this characteristic are single stars. And another idea was that maybe it was caused by starspots. But I think this was actually very, very clear, the answer to this one, in a 2017 paper by Willy Santiago. So Willy Santiago looked at a source, it's a weak-line T Tauri star. It means that it's a young source, only 2 million years old, that does not have a disk. So it's a 2 million years old source that does not have a disk, which means it has no accretion onto the star. So there should be no like hotspots. And it was known to have a strong magnetic field, and at the time it was very, very well established by many different spectroscopic work that this star has a temperature of about 4,000 Kelvin, measured from the optical. Okay, so Willy Santiago, they just obtained high resolution and low resolution spectra of this source, and they were able to match the optical part. Here is a bit on the red side, let's see the optical spectrum with a temperature of roughly 4,000 Kelvin. Well, but then when they look at how the infrared counterpart looks like, so how well can this 4,000 temperature fit the infrared part, they notice that it actually doesn't do a very good job. So they say, okay, let's try something cooler this time, right? They know that there's this difference in wavelength and temperature that we should use. So they use a cooler spectrum of about 3,500 kelvins, and they obtain a much better fit. But then when they look back at what that spectrum looked in the optical, yeah, then they encounter this. So as you can see, there's going to be a substantial difference in the strength of the lines, mostly here, which means that none of these two is really a good match simultaneously to the optical and infrared part. So that's a problem, and the way they solve it is by saying, okay, let's assume that the star is not covered by a single temperature. Let's now think that maybe these stars have two temperature components. It's not two stars, just one star, but with two different temperatures on the surface. And by doing that, they were able to get a much better fit to both the optical and the infrared region. Now, the temperatures they have to use are about 4,000 Kelvin for the hot part, but for the cold part, it's actually very, very cold. That's less than 3,000 Kelvin. And the really surprising part is that for this one to work, the star should be covered 80% by spots. And 80% is actually a huge fraction, right? It would be really hard to tell what's a spot when you have 80%. So let's go back to a more familiar case, which is the sun.
Please go back.
Yeah.
So I talking about hot spots. Please go back to the last page.
Yeah.
So you are talking about go ahead. Yeah, covered by spots. Are you talking about hot spots or cold spots?
Yeah. So this is it's a two temperature model. So they have a cold and a hot part.
Yeah.
So the thing is that the hot part, it's hot spot or cold spot, it only means sense relative to what? The hot part of the photosphere just is going to be matching the spectral type that was derived from the optical, while the cold part doesn't match anything that we know.
One question about this thing is just kind of understand the time, because this is like 2017 published study, but I remember that like long time ago when I was a freshman, they even talked in our university, they talked about like these last star spots.
Yeah.
So what's the new thing in this compared to this sort of older?
Yeah, so people knew that spot exists in stars. That's a very known for a very long time. Actually, we use them to measure periods, for example. Period rotation comes from this.
Yeah.
The thing that people don't notice is what's the effect of the temperature and how really spotted they are. Not many people will agree that a star can be covered by 80% of spots. You know, you can assume a small fraction. It will have a not very strong implication on the overall structure of the star.
Okay.
So yeah, but it's true. I mean, people knew that there were spot stars. It's not a surprise thing for anyone.
So for canonical studies, any difference between the temperature and the coverage?
So this is actually just a low resolution spectra they got. They have a high resolution one where they measure the temperature as a function of wavelength for H and K band. and they do have two best fit values. So there's a little bit of degeneracy, but the ranges of the 80%, the lowest they can get is about 76% spot coverage. And that actually, they realize that depending when you observe the star, some of the line will change a little bit. It cannot be extinction or disemission because it doesn't have a disk. So they think it's some kind of modulation of the rotation of the star. Yeah, so even when you observe it at a different time, the star seems to be super, super spotted anyway. Yeah.
Yeah, another question. I mean, 80% of the study is covered by, I assume it's covered, 8% of the study is covered by cold spot.
Yeah, cold spot.
How can you discriminate between 80% of the study is covered by cold spots or 20% of the study is covered by hot spots?
Oh, it's the same. Yeah. So the total fraction of the star should be 100%. So 80% is one temperature, which is the cold side. But I mean, you're absolutely right. It's just nobody would expect that this temperature, the temperature of the star, is less than 3,000 Kelvin, when it was very clear for decades that this was a relatively hot star. It's a good question. Okay, so this is the sun. Actually, this is the sun this week. We have a few spots right now, in case you're interested in looking at the sun. And something you can notice is that the sun has a few small dark things, right? Those are the spots in the sun, and we know these have cooler temperatures than the ambient photosphere. The ambient photosphere is going to have a temperature of about 5,800 kelvins. The spots themselves are about 1,000 Kelvin cooler. And the reason they're cooler is because of magnetism. So magnetic fields created in the center of the star will rise, creating some localized, darker, and more magnetic regions that we know as full spots. But in the sun, the coverage of these spots only reaches about a few percent during solar maximum. It can be way, way less during solar minimum. So if we imagine that we have the sun and place it like very, very far, and we will observe it, we will not be able to detect any of the spots and actually nothing about the magnetic field. This is actually very small. The fraction covering the surface is actually pretty tiny. But that is not the case of the calcium-4, where they found that the cool spot fraction was about 80% of the star. Yeah, so it will be maybe looking like this. Okay, that's not 80%, right? We can agree on that. How about that? So it just, the star itself will look like a giant spot. It's a giant spot. It's only 20% that is not the cold part. It's actually very, very, very small fraction. Now, that's maybe very interesting or nice result, but it actually has more profound implications that you might think. So this is an HR diagram where we have luminosity in the y-axis and temperature in the x-axis. Temperatures go this way. And we can use HR diagrams and stellar evolutionary models to go from temperatures of stars to masses of stars. That's something we do all the time in astronomy. For Lie calcium-4, it was known through many studies that this star was relatively hot, 4,000 kelvins, that will correspond to a mass of about almost 0.8 solar masses. Now, these new results in the infrared, they indicate that the temperature in the K-band is much lower, about 3,300, therefore a mass of 0.2 solar masses. But none of these two temperatures really matter in that regard. What we really need to have is the effective temperature of the star, which when we have more than one temperature component, can be calculated like this, which is a weighted average of the two hot and cold components, where we have the fraction covering the star being a very important factor. And for this star in particular, with an 80% coverage, this will mean that the effective temperature of the star is going to be very close to what we measured in the K-band. So for decades, we thought this star was a 0.8 solar mass star. Now we know it's closer to a 0.2 solar mass star. This is an error of factor 4 in mass measurement for young stars. It's not a 10, 20, 30%. You can see here from this plot that people thought that, okay, this is the temperature of the star, maybe it has an uncertainty of 50 Kelvin, 100 Kelvin. That's an uncertainty of 0.1 solar masses. But this is a factor of 4 different. And I'm going to be very emphatic that this is not just saying that we have an extra error of a factor of 4. This is a systematic change in the measurement of the temperature and has an implication for the masses of the stars. And of course, if we're measuring wrong masses, then that means that all the other things that we derive thinking we have the right masses are going to be wrong. So I think this is a very, very valid question to ask. So the question is Lee calcium-4 some weird star that we hope we never encounter again? Or is Lee calcium-4 really representing what happened in young stars that are strongly magnetic? Basically, have we measuring wrong masses for all this time in astronomy, young stars in the optical? So to answer that, of course, what we need are more observations, especially in the infrared, because optical temperatures are known. We have been taking them for many years, for a very long time. Infrared observations of temperatures are actually not available forever. And I've been using the NASA infrared telescope, the IRTF, on Mauna Kea, that's in Hawaii, where I got my PhD. And we use ASIAA. This is a high-resolution infrared spectrograph. ASIAA was commissioned in 2017, and it was at the time one of the few instruments in the world that can perform high-resolution infrared spectroscopy using actually a very wide band. So we can measure many lines at the same time. This is the sample I obtained. It's more than 100 sources, but for this study I only used 40 of them. And we selected sources from Taurus and Ophiuchus. These are young star-forming regions. And we select some of the sources that have dynamical masses measured from ALMA. And I'll go back to that point at the end of my talk. Roughly, the masses of the stars go between 0.3 to 1.3 solar masses. So, actually, I'm going to answer right away the question I just put regarding whether Lee calcium-4 is a unique case or is a more general problem we have in low mass star formation and low mass stars. The answer is that magnetic fields are actually the common thing in young stars. For all these sources, we measure magnetic fields of 2,000 or 3,000 Gauss. That's over 1,000 times stronger than what we measure in the sun, which will create large star spots, which will create temperature differences between optical and infrared observations. That's some example cartoon-ish representation. Now, what I will tell you now about is that how significant are those temperature differences, what are the implications for the masses, and right now, how do we measure those temperatures using ASIAA and synthetic models? Actually, very briefly. So this is the spectrum of a T Tauri star, CY tau. We go from 2.1 microns to 2.3 microns. That's the K band in the infrared, and we see many photospheric lines. So those yippings we see there are the photospheric lines. We're looking at the photosphere of the star. We're not looking at the disk or the material around it. It's really we're looking at the star. Those dips here, the spectral lines, carry a lot of information about the physical properties of the star. For example, we can use the silicon titanium line right here to measure the temperature of the stars. The relative strength between silicon and titanium will tell us what's the temperature of the star. And that also, we can use many other lines for that. We can use sodium right here to measure what's the gravity of the star. That's going to be important when trying to determine the ages of the star or how big they are. We can measure the rotation of the stars using spectroscopy. A star that rotates faster will create a broader profile of their spectral lines. And we can use magnetic field from the titanium line here, which through Zeeman effect, we can measure how strong are these magnetic fields. And we want to measure that because we know there is a correlation between the magnetic fields in the stars and the spots. That's how we really measure, there's a connection between those two. Okay, so after we collect this sample, analyze all of them through this method, we then want to answer the question of, well, how the rest of the sample compares to the calcium 4. So this is the calcium 4 right here. We know it has an optical temperature of about 4,000 Kelvin. The difference between the infrared and the optical temperature is around 600 to 700 Kelvin. And if the stars have no difference between these two temperature measurements, it should be around 0 right here. But that's not the case. Actually, in many stars, in most of them, we see that there's a significant difference in the temperature when you look at them between the optical and infrared, similar to the calcium 4. And what is more interesting is that there is a trend, right? Not all the stars are affected in the same way. Hotter stars, more massive ones, will have a larger temperature difference than the much cooler ones. At around a spectral type of M4, so 3,500 kelvins, this difference becomes actually quite insignificant.
So your sources are not associated with infrared X-rays? So your sources are not associated with infrared X-rays?
Yes, some of them they are.
Okay, but you have produced the effect?
Yeah, so the measurement of the temperature comes from the photosphere of the star itself.
Okay.
So things like infrared veiling and rotation and magnetic field are all taken into account in this model. Yeah.
Okay.
Yeah, and these are continuum normalized, so we don't worry about extinction and things like that.
Okay.
Yeah. So, okay, this is showing that Lie calcium 4 is not unique. Actually, this is a generalized problem in star formation where we look at different temperatures, different wavelengths, and we have different temperatures. Now, this is also a magnetic effect. So we also measure the magnetic field strength of the sources, and we try to correlate the field strength with the differences in temperatures we see. And although it's not as a nice correlation as I would hope for, I would like them to be, there's still a small trend of stronger magnetic field, which will imply larger temperature differences. So this means that either the spots are larger on the surface or they are cooler. Right? There's two ways you can produce this effect: larger spots or cooler spots. The next thing I will talk to you about is how these temperature differences will influence the masses we measure in stars. So if I were to plot my whole sample in a nature diagram, this is the theoretical nature diagram. We have gravity in the y-axis and temperature in the x-axis. I have plotted some evolutionary models from Faden 2016. We can have a direct connection between the temperature of the stars to the masses. Right? These mass graphs means that if a star started like here, it should just evolve almost isothermally contracting, right, through the highest term. What you can see from here is that the optical measurement of the temperatures, the blue points, are all shifted towards hotter temperatures, which will mean that we will derive or infer higher masses. The infrared temperatures of the same sources are generally shifted towards cooler temperatures, which means we should derive lower masses, smaller masses. So it goes like this. An optical temperature gives me an optically derived mass. An infrared temperature gives me an infrared derived mass. But there's no such thing as infrared masses or optical masses. The mass of a star is just the mass of the star, right? So we need to know which of these two temperatures is really giving us the right mass. So which of those two really approximate better the mass of the star. luckily, some of our sources have disks, and when they have disks, we can look at the rotation motion of the disk, the gas, to infer through Kepler's first law what's the mass of the star, and that is completely independent of this temperature thing here. So this is a way of testing if the true mass of the star is it closer to the optical temperature, or is it closer to the infrared temperature, the infrared derived mass. Okay, so this is the last plot of my talk, the last difficult plot. And what we have here is I'm showing how different is the expected mass when you use optical observations as a function of the true mass of the star. Right? If they're around 0, that will mean the optical temperatures are great for measuring masses in stars. But this is what we have. There's a substantial shift in the predicted masses versus the real mass of the star. On average, for the range of 0.3 to 0.5 solar masses, we are making 100% error. So if you think your mass is 1 solar mass or 0.5 solar masses, it should actually be half of that. So that's a big difference right there when we're trying to do very high precision measurements of some stellar parameters. In some cases, you can see that it can go all the way up to about almost a factor of 3 in the mass. When we look at slightly hotter sources, then we see that this trend is maybe a little bit less important, so it becomes less of a problem. But we still see an average difference of 12% with an actually very big scatter, right? We still have some sources being off by 50% at least. The question is, are infrared observations better at this? And I think they are. It's not only that in the infrared we see to be closer to the 0 line of perfect correlation between what we derive from the infrared and to the true masses, but they also have a much smaller scatter. So in the range of 0.3 to 0.5 solar masses, we're only over-predicting by 30% instead of the 90%, and in the rest we're under-predicting the masses by about 8%. So my take on this is that if you happen to have observations that you're trying to debate whether to use the optical temperatures or the infrared temperatures to measure the mass of the star, I'll suggest you use the infrared ones. They, on average, will give you more precise values, better values for them. Of course, I need to mention that this is actually, this particular plot depends on what specific model you use. I'm using the faded models, which are magnetic models, and those are known to be really good because studies like Simon 2017, Simon 2019, and even a study here by Professor Brown, Seaway, and Patrick already show that at least for this range of masses, the faded models are the best we can possibly get. So the main message I have is right here.
Just one question. So for your work, are you able to derive the fraction that you showed before, the F?
No, and I'll tell you now why. The reason I cannot derive a fraction for the stars with this is the following, and that's, I think, why we can still need to work on this. I mean, assuming that two temperatures, we've been thinking that two temperatures can represent the fraction of the cold and hot spots. But T Tauri stars actually are not only two temperatures. For T Tauri stars, we see accretion. Accretion will mean we have hot spots. And studies have suggested that between 1 and 10% of the star can be covered by these hot spots that can get to temperatures of about 10,000 Kelvin. So they are a small A star on the surface of our much lower mass stars. So if you want to really answer the question of how spotted these stars are, and we want to compare those against models, we need to not only look at 2 temperatures, but 3 temperatures. But for that, we actually need more data, simultaneous optical and infrared data where we can really get this really hot component. So I think because of that, we have really a way of moving this field forward at ASIAA. At ASIAA, we have access to many different telescopes. We can use CFHT, they have high resolution optical and infrared spectrograph. We can use Subaru, they also have optical and infrared. And we can use iShield in the infrared because that's available to anyone who wants to apply for that time. We need to use a multi-temperature models, it's more sophisticated than what we have been using. And of course, with the expertise of people here that know about how to do with ALMA observations, there's many people here, Siwei, Mayang, Yinxi, that can really do some change in this field. And with all of that, we should be able to put actually more stringent constraint on stellar evolutionary models. Because until we don't know the whole temperature structure, how much is covered by what, how much is the cold component, how much is the hot component, we cannot really derive an effective temperature, which is really what we need to constrain models of stellar evolution. Well, so I think that's all I have to say. I'll take questions now.
Yeah.
So, in your optical measurement, so in the young stars, it is quite obvious that your optical measurement you cannot access whole emission from the photostar, right? So not actual whenever you are trying to measure the temperature from optical data set. So it is quite obvious that you are not getting full information from that because of the extinction around it, right?
The extension? Yeah.
Veiling.
Oh, the veiling, yeah. So when we use spectroscopy, veiling is not really relevant because you usually look at the ratios of lines. So for lines that are very close together, veiling that's usually wavelength independent or very, very dependent will not be a problem. Or same with extension. You often correct for those things. Yeah. So most people will correct for those things before deriving a spectral type. If you use something like photometry, I agree, that would be wrong. But for young stars, I don't think people use photometry to derive spectral types.
Yeah, thank you for next talk. And I'm wondering if you have any physical interpretation, if data we want about why infrared spectroscopy works better for the measurement of the temperature and therefore the stars.
Yeah, so I think the reason for that is I think it relates to this slide right here. Sorry, take a little bit of time. I'll get there, promise. Yeah, so if we consider that these stars have only two temperatures, right? They just forget they are accreting for a moment, or maybe they're just not accreting that much. The temperature of the cool spot might dominate over the hot spot if the fraction covered by cool spot is very large. In the case of the calcium 4, that's the case. This is not accreting. And the effective temperature, which are these two boxes here, they measure two of them because of some uncertainties and shifting the observing dates, they will be much closer to the K-band. And something I didn't stress enough, optical temperature does not mean hot component, and infrared temperature does not mean cold component. If you measure something in between, you're going to have another observation right here. Those are not exactly the same things, but as long as the stars are heavily covered by spots, it seems like infrared observations trace better the effective temperature of the star, but that's a matter of how spotted they are. And because they show that for a blind sample, that's also the case, we can infer that in general the stars are going to be heavily spotted, although we're not really accounting for other effects like accretion and so on.
Yeah, but for example, so let's have a look at our sun. Okay, so
Yeah.
Cold are kind of special sort of so
Yeah.
cooler than so it should be, they should be because of some reasons, right? And most of the photographic emissions trace the correct temperature as a mean sequence star.
Yeah.
So in this then suppose if so in the infrared, so emission can be more affected by cool spots. So maybe there is something some mechanism to make it cooler.
For spots themselves?
Yeah.
So the way in the sun spots are cooler is because when you have magnetic field, you cannot have convection. So the outer layers of the sun are convective layers, but magnetic fields will completely freeze the convection and will not allow the material to bubble up. So the way that it radiates that energy is not radiation, it gets frozen.
So the same could happen for the premium sequence stars.
Exactly, and something I didn't mention either is that these stars, the premium sequence, are almost fully convective. Most of them are going to be fully convective, so the whole magnetism will not only change the surface of the star, actually it affects the whole internal structure. And some papers have shown already that these stars are bigger and cooler than we have predicted before because of the strong kilogauss magnetic fields they have.
Another question, so in your sample it is mostly like, is there any classification, observational classification like T Tauri, or it is from early class 0 to T Tauri? Is there anything?
So the sample goes from 0.3 to 1.3 solar masses. Those are all T Tauri stars. Some of them are classical T Tauri stars, and then there's a few weak line T Tauri stars. Some sources do not have this. But they're not really hot sources. I think the hottest one we have measured is in the optical is 5,000 Kelvin, in the infrared is 4,000 Kelvin. So there we see a huge temperature difference. That's actually, that source is called T Tauri. That's the one that gave the name to all the T Tauri stars. It's actually a very, very weird special case.
Okay, and in one of your plot you showed some deviation of in the optical, and that percentage you showed that with different kind of mass have different kind of boundary, right?
Mm-hmm.
Somewhere it is 31%, somewhere it is -8%, right?
Can you repeat that again?
Can you go back to your plots where you show the difference between dynamical mass and?
Yeah.
So in the lower mass region, the difference is higher, right?
Yeah.
In optical as well as in infrared.
Yeah.
So is there any physical significance?
Yeah. This means that probably the models themselves, so this is a way of testing this model. Actually, it works relatively well between half a solar mass and 1.3 solar mass. Actually, that's the conclusion of a series student paper in 2021, where they say this model is the best when you start considering from 0.5 and on. And they actually notice it. Wow, there's a huge difference. But even that difference becomes much smaller when you use infrared observations. So there's actually an advantage. Even if you take the wrong model, apparently, it's much easier. Or you get a less wrong answer, if you want, when using infrared observations.
Nice talk, thank you.
Nice talk. Just a kind of a comment about some of these mechanisms, of physical mechanisms that, we don't, of course, this is a contested thing, certain people are ferociously fighting about it somewhere in the material stuff. But you don't necessarily need like a flux tube type of a situation. You can generate a starspots. You can also generate it out of some certain turbulent stratified stratification instabilities, like negative effective magnetic pressure instability, for example. So you don't necessarily need like a flux tube rising up and then going up to generate these sort of things. Of course, people are very ferociously fighting about this thing. So, but I've been working on the turbulency.
That's very interesting. I didn't know actually, because I was just using the solar case, but so there are more mechanisms.
Yeah, also in solar case.
Also there. Yeah. But it's still debated whether it's true or not.
They are fighting about it. Yes. This is because the problem is that even in case the sun, we can see the sun, we cannot see it down there.
Right. That's very interesting. Thanks.
Hi Christian, thanks for the very nice talk. So I was wondering, can the hot spot or the cool spot, can it get revert back to the another state? Like, can a cool spot revert back to the hot spot? And if so, then what mechanism should go in that spot to make the cool spot to go back to the hot spot, or maybe to switch between two states?
So the question is whether a cool spot can become a hot spot?
Yeah.
Okay, so I'll say I think they cannot. The hot, so the cool spot, the really cool spot, same as in the sun, they are caused in some interpretations by just this flux flow. So there is a freezing of the convection, and you do not allow to escape much radiation, so it will cool down. That thing will change over time. You know, in the sun, the cool spots will migrate and they will disintegrate in some period right around the sun, so they can become the ambient photosphere, if you will. Now, the hot spots on the surface of the star are because of accretion. The star is still eating some material, so the hot really comes from shock material from the disk impacting the surface of the star and creating this really, really hot region. So those two are produced by magnetic fields, but in very different ways. So I don't think they can really one merge into another one. Yeah. They will shoot both of them eventually become, or they can become the ambient photosphere temperature, but not one to the other. Yeah.
But just to interject, so both theories I mentioned will result in having strong magnetic fields locally, which will cool down.
Okay.
It's just a matter of where it comes from.
Okay, I see.
Can you use the UV axis to measure the hotspot percentage, the coverage?
Yes, yeah, so people doing this research in the 1990s, and that's the latest I've seen, exactly, they use a UV part to see how much UV excess you have to try to correlate to a hotspot region. That's where they get, it goes from 1 to 10%. The question is that it's a bit difficult because, you know, accretion process will change in a very short time scale. So the sizes of your spots might vary from, I don't know, day to day or month to month, or I don't know how rapidly this thing can change. So it's not that we can just say, okay, this star in 1980 had a hot spot, let's take an infrared spectrograph and try to do this. Ideally, you want to get a simultaneous one, something like X-shooter, and get it from the UV all the way to the infrared, and so you can use 3 different temperatures. But that's a great solution, just using the UV to get a hotspot.
Any more questions?
I didn't quite follow. When you say you measure the magnetic field, where is it measured exactly?
Oh, where? It's on the surface of the star. It's the average unsigned magnetic field. We look at the splitting of the lines or the broadening because of this Zeeman effect.
So does this depend on the orientation of the inclination of the star?
It does not really depend on the inclination of the star. Yeah. So people looking at that kind of thing do polarimetry, and they will look at the line of sight magnetic field. In the measurements we do, it's really what's the magnetic field on the surface of the star, almost regardless of the orientation. And we cannot even distinguish which is this large magnetic field, like like the dipole or something like that, or is just a localized magnetic field. It's just really it's a one measurement. This star has on average this strength.
Just make sure that there's no possibility that the infrared and the optical are looking at the different layer of the photosphere that makes the difference temperature.
Yeah, so actually I've been wondering about that, but the curious thing is that when you look at non-magnetic stars like the sun, you do not detect these stars differences. So if you look at many stars, main sequence, M-dwarfs, that are not magnetically active, or you measure them in the optical and infrared, and you will not get 800 Kelvin temperature difference. Yeah.
So are there any scalar evolution model considering spots?
Yes. Yes, so there's one new, brand new, so the 2020 study by Garrett Summers where they look at evolutionary considering spots. The thing about them is that they consider spots covering 17%, 30%, 50%, and 80% of the surface. But they have this no way of telling which one is the right one. There's not enough people doing this kind of work. I know actually Yuka has been doing some work on modeling the spots on the surface. She's a student at NTU, a PhD student. And that kind of work will really tell us whether these models are correct or not. But again, those consider 2 temperatures. 3 temperatures seems right now too much. But I think we can really push that away and get ahead of the people doing modeling, so we can push them to release better and better models every time.
Do you have any comment on the station for the more massive stuff? And another question is, I'm wondering the surface area fraction of the cool spots, and what the differences of the region could depend on the initial mass and or evolutionary stage.
So first the higher mass sources. So I think I only go to 0.3 solar masses. For the high mass sources, so I think that's very interesting. Your question. Let me show something first. I think what is interesting is that we see larger temperature differences for larger stars. So if we extend this, we see infinite temperature differences for very massive stars. The problem is that once you become too massive, you lose your ability to create magnetic fields. So in young stars, magnetic fields are created in the convective layers of their atmospheres, or their internal structure. For most of these stars, they are fully convective. Then you increase your temperature, and you slowly start developing a radiative core. I'm not completely sure. It really depends on the age of the stars, the precise age. But at higher masses, your radiative layer will become so your star will become almost fully radiative. And at that point, it's really hard to sustain such strong magnetic fields. I have a program trying to investigate a bit further this region right here of slightly hotter sources. So that's a really good question. And the second question was about the evolution,
the fraction of the surface area can be depend on the evolutionary stage. For example, main sequence or later phases, it could change.
Yeah. These stars, however, they're all about the same age, 2 to 5 million years old, maybe 10 million years old. So their evolutionary phase is pretty much the same. This effect, however, as you were saying, it will disappear once they become a main sequencer for the most part. We know that M stars are magnetically active for much longer because, again, M stars some of them might never develop a radiative core. So they stay fully convective, they can still play the dynamo mechanism to create magnetic fields. At some point, it will slow down enough that dynamo will not do anything. But yeah, so there's a relationship between the magnetic activity and the age of the star. And I'm working on a paper showing that up to about 100 million years old, your stars will have strong magnetic fields. Very strong ones, similar to the T Tauri stars.
Okay,
Any more questions?
So do we still see a difference in the infrared versus minus optical temperature for, let's say, like a M-DOF, which is, let's say, a few giga-years old? Or does that totally vanish by the time it's in a few 100 million years?
Honestly, I don't know. So the thing is, you can see here that for the very cold ones, the temperature differences start becoming actually smaller, maybe only 100 Kelvin. You will make really precise measurements to tell whether that's significant or not. You might want to just do the proper two temperature modeling for these sources. it's known that stars, M stars, less than a year old, will still have very strong magnetic fields. So it's possible, but if the star itself is so cold, maybe the spot cannot be much cooler. So maybe, despite it has spots, maybe just the temperature difference will be really hard to reach. Yeah, it's possible. And we really don't know what happens here. I guess that becomes zero, though not really proven.
Okay, so it's about time. So let's thank our speaker again.